This is Lisa Knight, and I just wanted to give you some feedback on your math review or Chapter 1 quiz. I was looking through it, and I just want to go over 4 problems, which are pretty common problems that people had in the homework. And the very first one I noticed was number 10 in section 1.2, and that was the one where you had to convert the blood flow problem of 5 liters per minute to meters cubed per second. So let's kind of go over that problem. And basically all you had to do was convert the liters per minute to meters cubed per second. So the best way to do this is to use a factor label or a conversion grid where you list the 5 liters per minute as a fraction, and then you first choose the conversion factor to convert minutes to seconds, and I chose 1 minute equals 60 seconds. I put my minutes up top here and my 60 seconds on the bottom, so that when I multiply 5 liters by 1 minute and divide by 60 seconds, what happens is the minutes are going to cancel out and leave me with 5 liters per 60 seconds. And so if I divide via 5 by 60, that's going to give me liters per seconds. In addition, I can go ahead and convert my liters to meters cubed. I looked up the conversion using Google, and I saw that 1 liter was 0.001 meters cubed. And so I put 0.001 meters cubed up top and put 1 liter on the bottom, so it would cancel up or cancel out the liters up top. So now when I multiply the 5 liters by 0.001, I'm going to be left with meters cubed. My answer should be 8.3 times 10 to the negative 5 meters cubed per second. When you type that into OpenStax, probably the best way to do that is 8.3 e negative 5. The e just replaces typing out times 10, and then meters cubed per second. Or you could put it in as a decimal value. In number 15, this is a very common type of question that students have problems with, so don't feel bad if you had a hard time with this. A couple of you got it right, but a lot of you only got it partially right. So using dimensional analysis is really important in science because it means that you're putting down your units in the problem and that you're thinking critically about how your variables are interacting with each other. So what we want is we want the units on each side of the equal sign to come out to be the same. So for example, if I multiply mass by velocity and divide it by time, and the equation says that that is going to give me force, then the units on this side of the equation should be equivalent to the units of force. The units of force are kilograms times meters per second squared, and that's something that you're going to need to memorize. The basic standard units of mass that we use are kilograms. The units of speed are meters per second, and the units of time are going to be in seconds. So if I mathematically treat these units over on the left here like numbers, when I multiply and divide these units, I should end up with kilograms meters per second squared if this is dimensionally correct. When I divide by a second, I'm really multiplying by the reciprocal. So when I divide by a second, I'm really multiplying by 1 over a second, which means that I'm going to end up with kilograms meters over seconds times seconds, or seconds squared. So yes, this is dimensionally correct. The other equation though, xv squared equals vx cubed all over x squared, is not dimensionally correct. So the first thing I'm going to do is simplify it. If I do that, I see that it simplifies down to xv squared equals fx. Well, just common sense tells me that v squared probably isn't going to have the same units as f, because f is kilograms meters per second squared and v is meters per second. There's no kilograms on this side, so just outright in my head I should know that this isn't going to work. But to prove it to you, I put the units in. X is distance, so it's measured in meters. V is meters per second, and I'm squaring it. F is kilograms meters per second squared, and X is m, meters. When I multiply these through, I get meters cubed over seconds on one side, and I get kilograms meters squared over seconds squared on the other side. So this is not dimensionally correct. And the last equation is the one most of you guys did not get. So let's really pay attention to this and see why it works. X times t is m meters times seconds. V times t squared is meters per second times seconds squared. A times t cubed is meters per second squared times seconds cubed. If I do the math on the right hand side here, I get meters per second times second squared is a meters times a second. And I get meters per second squared times seconds cubed is a meters times a second. And these, I can add these two things. This is an apple and this is an apple, right? They are the same units. These are the same quantities. So in the end, the units on the right hand side will be meters times seconds, which is the same as a unit on the left hand side. So yes, this is dimensionally correct. In number 20, you had to convert the speed of sound to kilometers per hour. And this is a two-step process. You had to go from meters to seconds to kilometers per hour. So you had 342 meters per second, and then I first changed that to kilometers. There's 1,000 meters in a kilometer. I put the kilometer up top and the meters on the bottom to cancel out. Then I looked up what an hour was in seconds, and it's 3,600 seconds. So put 3,600 seconds up top and an hour on the bottom. When I do that, I get 1231.2 kilometers per hour, and it wanted the answer in scientific notation. And that answer should be 1.23 times 10 to the 3 kilometers per hour. And the last one I want to go over is the plate tectonics problem, where it told you that the seafloor was spreading at a rate of 4.0 centimeters per year, and it wanted to know how far it moves in 1 second. Well, that would be easy if I know how fast it's moving in centimeters per second. So the first thing I did is I changed this to I messed this up and I'm very sorry about that. I changed this to centimeters per second, and what I should have done is I should have divided this by and that was totally my fault, and I apologize for that. And let's see if I can edit on this. Maybe not. We'll see. Maybe I can make a... Okay. So this should be 4.0 centimeters per year times 1 year over 3.15 e to the 7 seconds. Okay, so I should have flipped that around, and I hope you guys see why, because I want the seconds on the bottom and I want the years to cancel out. So right now, the way it looks is like I want to get years squared. So if I do that, then my new speed is going to be 4 divided by 3.154 e to the 7, which is 1.268 e to the negative 7 centimeters per second. And to figure out how far that travels in 1 second, I just multiply by 1 second, and that's going to give me 1.238 centimeter e to the negative 7 centimeters. So it doesn't travel very far. That's why it takes so long for the tectonic plates to move apart over time. So that would be the answer to A. Then the second thing I would do in that question is it wants me to find the movement rate and kilometers per year. So to do that, I'm going to change my centimeters to kilometers. Well, first, to change my centimeters to kilometers, I need to change my centimeters to meters and then my meters to kilometers. So the first thing I did is I went from 1 meter to 100 centimeters, So I divide by 100 centimeters to turn this to meters per year. And then I know that there's 1,000 meters in a kilometer, so I divide it by 1,000 meters to turn it to kilometers. And I get a speed of 4.0 times 10 to the negative 5 kilometers per year. So once again, very sorry about the mistake here in this paper, but it should save when I save it and upload it for you guys. If there's any other questions, please let me know. I'll be glad to answer any particular questions you have and set up an appointment to meet with you. Have a great week.